Good morning, everyone. We're going to continue our lecture on chapter 11. And today we're going to talk about vapor pressure of solutions. So remember, we're talking about vapor pressure. It's the pressure of the vapor that's over a liquid at equilibrium. So what you want to think about when you're thinking about vapor pressure, you want to think about your water bottle that many of you carry around to your classrooms. If you were to keep that water bottle partially empty, like it's only half full, and you keep it closed, eventually you're going to see droplets forming on the inside. Well, once that's equilibrium, you're going to have just as many water molecules trying to escape the liquid as many water molecules that are losing energy and going back down into the liquid. That's equilibrium. And so we are talking about that pressure that's right above that liquid at equilibrium. That's vapor pressure. Vapor pressure of a solution is something that, quite frankly, we haven't had to worry too much about in this mild winter that we're having. But example would be antifreeze in our cars so that we can start our cars on cold winter days and they don't overheat on very hot summer days. Or salt on our roads and sidewalks so that the freezing point will decrease so that it will melt and we don't have to worry about things freezing on our roads or on our sidewalks. So vapor pressure of a pure solvent, again, think of solvent as water, is greater than the vapor pressure of a solution. So the picture you should have, remember, is that a pure solvent water, I just have those water molecules swimming around each other, and then I have the vapor pressure of a solution where I have some things dissolved. So it should make sense that there's going to be more interaction between the solvent molecules than there is when I have a solution. So it's going to take more to be able to get that to evaporate, excuse me. So what are some of the things? What are some of the things that we have to overcome? So one, we need to make sure that we overcome intermolecular forces. And if you've been looking at your text, you can see that they have been abbreviating this in the same manner. So we have to overcome those intermolecular forces, things such as London dispersion forces, hydrogen bonding, dipole-dipole moment. Those are intermolecular forces. The second thing that we have to overcome is that we have to make sure that we can gain enough energy to escape the solvent. So you need to gain that energy. If not, you are going to get out of that. Think of your water bottle again. That water molecule that's in the liquid phase is not going to gain enough energy to get into the gaseous phase. So we have to be able to gain that energy. I guess I only had 2 points. I'm sorry. So those are the 2 points that we need to talk about. Now, when we have a non-volatile solute, what a non-volatile solute means is that you don't have a bunch of interaction. So we're adding a solute and the particles are in the way of my solvent. So they're not able to vaporize as easily. So think about this. If I have a beaker and I have some water molecules and they're just in here having a great old time, moving around each other, just having a great little time in there being a water molecule. Well, then all of a sudden, remember, be the molecule like we talk about all the time, be that water molecule, then all of a sudden I'm adding some salt or sugar or whatever it is your picture is. Maybe we're making some Kool-Aid because we're always making Kool-Aid. Well, if I am this water molecule right here and I really want to vaporize, okay, and I have to gain and gain all this energy, I have to overcome forces. Well, in order to do that, I want to get from this liquid phase out of here to the gaseous phase. Well, if I'm trying to gain energy, and the way that I can gain energy is by colliding with other water molecules or colliding with the walls, well, all of a sudden I have something in my way. It's like a crowded room and you want to get to your friend on the other side of the room, but there's all these people in your way. It's going to take more energy for you to wander around and get to your destination. The same thing is happening here. It's not going to be able to vaporize as easily. And remember, they want to reach equilibrium. They want to reach where as many are evaporating as being condensed. They want to get to that equilibrium site. So obviously this is going to be a closed system that we are talking about right now, and I haven't really drawn that. But think of your water bottle that I told you to imagine at the beginning. So another way to study this is Rayold's law. As you can read, it says a study of vapor pressures of solutions, remember solute and solvent, containing a non-volatile solute for ideal solutions. Now, if we have an ideal solution, what that means is that my change in heat of my solution is actually equal to 0. So what you have is you have these two parts. There's not any interaction. My solute and solvent, I don't know if you guys still use this term or not, but they're just kind of chilling in there. They're just chillaxing. They're just by each other. There's no interaction. Remember, if it's an ideal solution, that's the way that we can study gases a little bit easier. So if we have that ideal solution, Rayleigh's law is saying that my pressure of my solution is equal to the mole fraction, remember mole fraction is part over the total, times the pressure of my solvent. And this is actually, they use P sub 0 here, and what this actually means is vapor pressure. So this is saying that my mole fraction times my vapor pressure is going to equal my pressure of my solution. And we can add more variables to this. If we have more than one liquid, it would just be adding this again. So how we know that we all don't live in the ideal solution world and very few things behave ideally, how are non-ideal solutions going to behave? Well, if there's going to be non-ideal, there's going to be more and more deviations. If you think about a polar attraction, you have all those charges and they're attracted to each other. We might have some hydrogen bonding to overcome. Well, if I have to overcome that stuff, it's going to take longer for those molecules to escape. And so that means I'm going to have lower vapor pressure. So think about that again for a second. I have this polar substance. They're attracted to each other. If they are trying to reach equilibrium and they want to get into that gaseous phase, it's going to take a lot longer to do that. There's going to be fewer molecules that are escaping, so that vapor pressure is going to be lower. On the other side is if I have non-polar solutions, remember those interactions are very, very weak. They don't have to overcome as much. And so the result of this is I'm going to have higher vapor pressure, higher vapor pressure, and because there's not as many attractions. So this will be displayed when we go through these example problems right here, and we'll do those in class. All right, so we're at about 7 minutes, so I think I'm just going to keep on going and finish this last little section right here. These are both really quick little things. Boiling point elevation and freezing point elevation. You have experienced both of these. They are called colligative properties. Colligative properties have been on and off the test, so it kind of depends, but they are worth mentioning. So if we take a look, we have boiling point elevation, freezing point depression, osmotic pressure, which we'll talk about here in a second. Properties that depend only on the number of particles, not the identity of the particles in an ideal solution. So what is this going to do? Well, this is the first thing that's going to do is it's going to lower my vapor pressure. Again, we have something in the way. We have particles in the way in order for me to gain all that energy that I need. It is going to lower my freezing point if I'm adding particles to a pure solvent. It's going to raise my boiling point, and we are going to study actually freezing point depression in class. And then the fourth thing is it's going to lower my osmotic pressure, and we'll talk about that in the next section. So these two little expressions that you see here, boiling point elevation and freezing point depression, go hand in hand. They basically mean the same thing. So our change in temperature is going to be affected by a constant, and Kb is noted as our boiling point depression constant. Boiling point depression constant, you should recognize this script M is molality of the solute. And then our freezing point depression, same thing. Our change in temperature is going to be reflected by our freezing point depression constant times the molality. Which one is more affected? Well, freezing point is going to be more affected by adding a solute than is boiling point elevation. So you guys have many, many examples of this, as we just talked about at the beginning. Boiling point elevation, you have that pan of water on your stove and you're trying to boil your macaroni and cheese, and you add a little bit of salt to this. Well, is it going to take a little bit longer to boil? Absolutely. Think about that. That water molecule has to get around that. It can't get out of here as quick as it would like, and so it's going to take a little bit longer. However, the difference on our boiling water is very, very slight, and you would have to do it on the microscopic level to really see the difference here. But down here in freezing point depression, you've probably seen this on your sidewalk. You see some ice building up, you add some solute to it, and it's going to lower that freezing point, and so now your sidewalk is clear. So the freezing point is more affected than it is by the boiling point than by adding a solute. So what that means, if water normally freezes at 0 degrees Celsius, most of our chemicals can go down, 15 to 20 degrees. And so that means that now it's going to freeze at negative 15 degrees Celsius. On the other side, if it boils at 100 degrees Celsius, by adding a little bit of salt, normally only increases it to 101 degrees, maybe 102 degrees Celsius. So it's not as big of a factor. And then we have this example problem right here that we will talk about here in class. All right, you guys have an awesome day, and I will see you later.